Now that we have covered the basic types of fasteners and joint types, let's take a closer look at the possible failure modes in a mechanically fastened joint. We are going to limit ourselves in this discussion to mainly shear type mechanically fastened joints. This is not to say that tension joints are not important within the aerospace industry. There are numerous joint applications where a tension joint is needed, and these need to be carefully designed as well. But generally speaking, shear joints tend to be more weight efficient than tension joints, and thus are more frequently used. We will center our discussion around the simplest form of a shear joint, a single overlap of sheets containing several rows of fasteners like the one shown here. This joint is known as a single lap shear joint. In order to understand the failure modes, it is important to understand the loads involved in such a joint. The primary means for this load transfer is through bearing between the fastener and sheets. A smaller portion of the load is transferred by friction between the joined parts at each fastener location. Finally, load that is not immediately transferred by the first row of fasteners it encounters flows around that row of fasteners to be transferred by later rows. This latter load is known as the bypass load and is analogous to the flow of people on a subway platform looking for the most efficient exit. Some take the stairs, others an escalator, and even others will take an elevator. People will bypass one means of exiting for another to create the most efficient flow of people out of the station. In addition to load transfer, secondary loads exist within a structure known as interference and secondary bending. The role of hole filling, also known as interference, was discussed in detail in a previous video. This can produce favorable residual stresses and influence the stress concentration due to load transfer. Secondary bending is another phenomenon that can generate high stresses. Due to the offset between the joint sheets, bearing loads on each fastener will generate a bending moment that causes rotation and bending of the joint sheets. As we will see later, the added bending stresses due to this phenomenon can be critical for fatigue failure. There are 5 main failure modes to consider when looking at the static failure of shear type joints. 3 failure modes related to sheet material known as net section tension, bearing, and shear tear-out failure, and 2 failure modes related to the fastener known as fastener shear and fastener pull-out failure. Generally speaking, it is undesirable for the fasteners to be critical for failure. There are a number of good reasons for this, but the most obvious is the fact that we select fasteners to join a structure together, and if the fasteners fail before the structure, then we simply selected insufficiently the fasteners for that application. Let's take a closer look at each of these failure modes. First, we will look at the undesirable fastener failure modes. Fastener shear failure occurs when the shear stresses in the plane of the fastener exceed the shear strength of the fastener material. This failure mode is typically unstable, as if one fastener fails, the load on all the other fasteners increases, leading to their immediate failure. Such an unstable failure is another reason why this failure mode is undesirable. Next, we have fastener pull-out failure. Due to secondary bending, fasteners within a joint will tend to rotate. If the bending becomes large enough, the resistance to rotation provided by the fastener heads can be overcome, resulting in the fastener over-rotating and being pulled through the parts it is joining. The first of the sheet failure modes we will look at is net section tension. This failure mode is a consequence of the tensile strength of the sheet being reduced by the row of holes drilled into it. The remaining cross-sectional area of sheet along these rows, or net section, is smaller than that of the total cross-sectional area of the sheet, but has to carry the same overall load. As a result, this net section region can fail earlier than the rest of the structure. If load passes the net section without failure, it has to flow around the fastener, creating a region of high shear on either side of the fastener. If the fastener is too close to the edge of the sheet, the area that can resist this shear load can be small enough that ultimate shear strength of the sheet material is reached. This results in a failure mode known as shear tear-out, where these high shear stresses effectively cause the fastener to tear a portion of the sheet completely out of the joint. The final failure mode is known as bearing failure. If the load can pass the net section and region of shear tear-out without causing either of the previous failure modes, it is still possible for the compressive stresses in the contact region of the fastener and sheet to exceed the compressive yield strength of the sheet material. This failure mode causes permanent plastic deformation within this contact region, resulting in elongation of the fastener hole. Bearing failure is the least unstable of the failure modes and thus is often the preferred failure mode to have critical in a joint design. It should be noted, however, that this is not always possible. If a joint is subjected to repeated loading below its static strength, it can still fail as a result of fatigue. Fatigue was extensively covered in an earlier unit, so the fact that cracks will tend to nucleate at the edges of fastener holes where stress concentration factors are high should come at no surprise. We have also already discussed how hole-filling properties of a rivet can actually help reduce these stress concentration factors. What is also important to consider with respect to fatigue of mechanically fastened joints is the role of friction and secondary bending. Both of these phenomena can greatly accelerate crack nucleation. Friction within a mechanically fastened joint is not perfect. Frictional slip between the surfaces can occur, resulting in rubbing between the joint sheets. This repetitive rubbing can cause wear damage known as fretting, generating a scar on the mating surfaces of a joint. If we look closer at such a wear scar under a scanning electron microscope, we can clearly see that the wear damage produces rough surfaces and even microcracks that can lead to nucleation of larger cracks. Secondary bending makes this location even more critical. The eccentricity in load path within an overlap joint results in bending that produces compressive stresses on the free surfaces of the joint and tensile stresses at the mating surfaces of the joint. The superposition of tensile bending stresses at the mating surfaces of the joint with the other stress concentration and the influence of fretting damage can accelerate crack nucleation. For this reason, special attention must be paid to these risks in a fatigue-critical joint design.